Ladies and gentlemen, welcome to a second video lecture on the Sun, derived from my book, The Fivefold Sun. The Fivefold Sun consists of 6 parts, and in video 2, after the introductory video number 1, we deal with the first section of the first part of this book. Part 1 deals overall with the numerical kinematic of the solar ball over the Schwabe cycle. In this companion lecture, recorded on October the 3rd of 2018, we introduce the topics that were discussed in volume 1 of the book, which was filed at the Bibliothèque Nationale de France in Paris in late 2017, a year ago. The work that was performed in this part 1 was done from 2002 to 2012, and it was not much updated after 2012, in spite or because of several revisions of the data sets under review, which were proposed from 2014 and 2016. For 2 reasons, these revisions were not taken into account systematically after this work was performed till 2012. The first reason is that I personally contributed to one of these revisions in Vaquero et al., published in 2016 in the journal Solar Physics, and I don't want to be interfering somehow as a referee of my own work. The other reason is that there are many revisions that were proposed. They are provisional revisions and they are conflicting. This page is a complete outline of the contents of part 1, in which you see section 1 of part 1 dealing only with the central tendency of the Schwabe cycle, its overall length. That's what we discussed today in video 2. The rest of part 1 will be introduced in further videos. As you see, the rest of part 1 is consisting in further investigations of lengths that can be found in the quasi-decadal solar fluctuation. I call the fluctuation, which is regarded quite widely as the main fluctuation in activity in the Sun, a quasi-decadal one, because I don't want to presuppose that the true, or let's say scientifically, the statistically characteristic length is indeed 11 years, or maybe in fact less, as Schwabe, who discovered this fluctuation, initially proposed, calling this cycle of a period of about 10 years. What is usually discussed in solar physics literature is a cycle of 11.11 years. This was determined by Rudolf Wolf in Switzerland, in Zurich, in the mid-19th century, more than a century and a half ago. Must be updated. But there is also an older tradition of a shorter solar cycle of maybe about 10.6 years. I call it here a Scottish cycle because 3 gentlemen contributed to this particular estimate, and they all come from Scotland. Lamont, Brown in the 19th century, and in the 20th century, the Scottish statistician Udny Yule. So what is the true length of the solar cycle? what is the statistically defined central tendency of the quasi-decadal cyclical length in the solar behavior? If we want to arrive at a rigorous determination of this intriguing quantity, we first have to solve a couple of methodological issues. Definition of what is in fact this fluctuation, this cycle. Definition of what is a central tendency in statistics. And when we know that, when we have found satisfying answers to these issues, then we can apply one or two methods to arrive at what we seek, looking at individual cycles and finding their central tendency, or using more sophisticated mathematical tools that can arrive at a synthetic value of a peak frequency for a periodical or quasi-periodical phenomenon. And when we have looked at the two options from individual cycles and from considering the entirety of a time series with a mathematical tool that determines its peak frequency, then we can arrive perhaps at the definition, the determination of a central value for the length of the quasi-decadal Schwabe solar cycle length. First of all, we have to define what the Schwabe cycle is. The physical basis, based on the original findings of Mr. Schwabe, Heinrich Schwabe, in Germany in the 1830s and 40s, is a number of sunspots or a number of sunspot groups. Nowadays, solar physicists rather look at physical phenomena that are magnetic in nature or that represent quantities of light that are being emitted by the sun. It was found that in a particular wavelength, in the radio wave spectrum, there is a particular wavelength which may be representative of the variation of all wavelengths in the solar spectrum. If we now compare the traditional, more primitive way of looking at activity fluctuation, the number of features at the surface of the sun, and the wavelength approach, we find that there has not been much of a departure over time in the curve of the radio wave amplitude at the decadal scale and the curve of the sunspot number amplitude at the same decadal scale, with some short-lived exceptions. So if we are comfortable with using the radio wave, for instance, in the time span where it has been available since the 1950s, and if we are comfortable to use as a proxy of these radio waves the sunspot numbers for the more distant future, we will be able to have a series from 1610, when Thomas Harriot first glimpsed the individual sunspots at the surface of the sun, to 2010. This is 4 centuries. And we have the longest extant physical series that is available to science. This is represented by two specific time series, RZ for relative sunspot number from Zurich, and RG for a relative group sunspot number. This alternative to the Wolf RZ number was defined in 1996 by Hoyt and Schatten. I participated in a revision of the collection of observations that is used to define RG in Vaquero et al. 2016. This is not taken into consideration here out of objectivity. We remain with the series that as they were defined until 2012. What is not used is the fossil terrestrial record, because it is not, of course, a direct measurement of solar activity. It is found at Earth and is prone to be perturbated by terrestrial factors, such as the radiocarbon record. It will be very, very interesting to understand and to find out what is solar amplitude variation at millennial timescales, but not for the last 4 centuries. Also, we will not look at geomagnetic data, not only because as much as the radiocarbon or other fossil data at Earth, they are prone to be perturbated by terrestrial factors, but also because they may be representative of something else, namely a poloidal or a polar solar cycle, whereas in fact RZ and RG, the sunspot relative numbers, they are representative of activity only in the toroidal region. Maybe these two regions are not representing the same fluctuations inside the Sun. The definition of a central tendency has to be performed to go beyond the mere notion of a mean length, which is what is being referred to in general in solar physics when the solar cycle length is discussed, because the value of 11.11 years that was defined and determined by Wolf, it is a mean value. But if you have in the distribution of solar cycle lengths some at least one or more outlying lengths, such as cycle number 4 from 1783 to 1798, more than 15 years, maybe 16 years, you have much fluctuating mean length over time, and you don't know which mean length at what point in time is the right one. Whereas if you look at a median, median is defined as the value above which there are as many units in the data sets as they are below this median value. It will fluctuate much less due to outlying lengths such as cycle 4, which I just mentioned. The mode is the value of a length bin in which there is the largest number of individual cycle lengths, and it is basically the same as a peak frequency, which is extracted synthetically with a mathematical procedure from an entire set of cycle length values instead of consideration of individual cycles to arrive at a mean, a median, or a mode. So the basic project in section 1 of part 1 will be based on individual cycles and separately on peak frequency to arrive at a definition of the median of the solar cycle length, which we find will be much more robust over time compared to a mean length. The conclusion is that if we exclude cycle number 4, we have a median of 10.67 years. If we include it as 2 cycles, we have a median of 10.6 years, 60 years, which is very small variation in the result. Whereas if we exclude cycle number 4, the average will be 10.83, and if we include it as 2 cycles, it would drop as low as to 10.59 years. So we retain the median as the statistically representative quantity to describe solar cycle length. In the case of excluding cycle number 4, again, in this entire table of all results that we are investigating, that are under scrutiny, we find 10.67. And we find that in most binning procedures, these are 3 different binning procedures, we have a unimodal result with a mode that is about 10.6 years. This is the same complete set of data of cycle lengths under consideration in the other case where cycle number 4 is divided into 2 cycles. Here you see a wrap-up of whether the found cycle is unimodal or not, and you find that it is overwhelmingly found to be unimodal. And it is unimodal with the value of the mode, which may be other than 10.6, but in many cases is 10.6 years, and thus is very close to the median value, which is close to 10.6 or 10.7 years as well. We look finally at results found by other authors for median lengths, and we see that they found on average, those authors that I was able to locate in the literature, they find on average a median length of 10.74 years. If I include my own results, these average out to 10.66 years. And if we look at the unimodal modes found by the very few authors who looked at a mode in the distribution of solar cycle lengths and found a unimodal result, they are about average out to a mode of about 10.63 years. If we look by comparison to the time distribution of solar cycle lengths from the 18th century to present, we will find that it has the average length has reached a length of more than 11 years only around 1901. Whereas in the 18th century, it was the mean length was as low as about 10.3 years. If we look more recently, we see that until the end of solar cycle 23, the average length was 10.93 years, and including now the cycle ending in 2008 or 9, cycle number 24, it has averaged out since 1712 to 10.99 years, which is somewhat short of 11 years. So, having determined these characteristic lengths from consideration of individual cycles, we now look at a synthetic central value from peak frequency analysis. We look at this in the relative sunspot number series, in the radio flux series, and in other sunspot index series, sunspot index proxies, including the sunspot area. If we look at the various techniques that allow to arrive at such a peak frequency, we see there are many. This is a short typology. There are the Fourier transform, harmonic analysis, pure spectra. Then there is the periodogram analysis with all its various typologies. And then there are the not Fourier transform derived techniques such as the least square analysis, maximum entropy, etc. And more recently, the state space, so-called state space models, including the model and the several models defined by Friedli in Zurich, a successor, so to say, of Rudolf Wolff, who in 2005 arrived at a peak frequency for the quasi-decadal solar cycle length, which is much shorter than Wolf's length of 11.1 years. If we now look at the entirety of the 19 results which I could locate in the literature, which arrive at some kind of peak frequency value for the quasi-decadal solar cycle length, we find that the average of these 19 results is 10.60 years, quite close to the median values that we could estimate from consideration of the individual cycles in the preceding pages. And if you look at the distribution, the spread of the individual values, there is a very little spread. So what is the end result of this analysis? We find that the central tendency of the Schwabe cycle length is not in the vicinity of 11 years, as is the means of this length, as determined since Rudolf Wolf within 0.1 year. It is instead less than 10.65 years. This was found not only by several investigators, independently of the research performed in the Fivefold Sun here, but also by Mr. Friedli in Zurich, who is again somehow a follower of Wolf in the same city in his analysis published in 2005. The mode may be of 10.6 years, plus or minus a few months. A final 4-digit estimate, if we need 4-digit precision for the central value of the Schwabe length, would be 10.61 years. And if we needed 5 digits, robust estimate would be about 10.615 years. This amounts to a range from 10.60 years to 10.63 years, with a half-width of 0.015 years. And that is the statistical basis from which we can now further investigate the length of the Schwabe cycle and the two legs, the rise leg of the cycle, the fall leg of the cycle, and in a further step interpret these lengths and their ratios in terms of the numbers of rotations of the solar ball. Thank you for your attention.